Hi everybody, this is Dr. Dogu. This time discussing on some geometric series GP convertible to discrete distribution DDs. Happy listening. Introduction. This video attempts to exhibit properties and usefulness of generalized GP convertible to DD. And we'll also see a couple of usefulness requirements. Just ensure that you've seen my immediate past two videos because the subject matter actually started from them. Synopsis. Here we will see a review of those past videos. Then we'll see a generalized DD. We'll see an application and we'll see the usefulness of having to do all this. Why do we need to do it? Is it just child's play or something? Then the review. Validity of type 1. By the time we listed the series, we saw that this is of type 1. Summation 1 all over 2 raised to the power I, which will sum to infinity to give you 1. 1 happens to be the numerator of the fractional part of this series. Take note of that. We do not need to divide by any number before we can get our PMF because it's already summing to 1. Now, its expectation variance and standard deviation are obtained through this means. We saw that expectation of x converge to 2, and 2 happens to be the denominator. Keep that as well. The expectation of x squared converges to 6. As such, the variance is equal to 6 minus 2 squared, which happens to be 2, meaning that the mean and the variance are both equal to 2. That's a property. If you've been working on distributions, you will know that that's a property shared with the Poisson distribution. With Poisson distribution, its mean and variance are equal. So we say that this PMF, this discrete distribution is Poisson in nature with lambda 2, lambda being equal to 2. All right. Validity of type 2. For the series, this is the series. You know, the numerator is the type. Okay. The first term A is equal to the common ratio equals to 2 over 3. And it sums to infinity to give you 2. Mind it, the numerator. Okay. The PMF is this. So the expectation variance and standard deviation are obtained. Expectation converging to 3, the denominator. Expectation of x squared converges to 15. As such, the variance converges to 6. And 6 happens to be the product of the numerator as well as the denominator. To be able to check the validity of this, be sure you have a powerful machine. Otherwise, it will give you a fake convergence. So the standard deviation is equal to square root of 6, which is 2.45. Okay, approximately that is. Then validity of type 3. For the series, it is this. First term is 3 over 4. The common ratio is also 3 over 4. As such, you sum to 3. Mind it, the numerator, like I used to say. So the PMF, so the discrete distribution is expectation variance and standard deviation are given. This converges to 4, which is the denominator. This converges to 28. And the variance as such is 12, which is the product of the numerator and the denominator. So the standard deviation is 3.46 approximately. Now we continue in that fashion. We continue like that until we come to the type 9. You will be saying that the sum to infinity will be equal to the numerator. The expectation will converge to the denominator. And then the variance will convert to the product of the numerator and the denominator. And then standard deviation will be square root of the variance, as usual. So that's the case. So what if we have the n-1 type? This will be the series, and it will converge to n-1. You can check the validity of this using packages, e.g. scientific workspace. Okay, so it will convert to the numerator, which is n-1, and the expectation will convert to the denominator, which will be n, which in this case is n, and then expectation of s squared will be this, such that the variance will be this, and the standard deviation will be that. What if it's the n type? If it's the n type, the numerator converges to n. Well, expectation converges to the denominator. Expectation of s squared will converge to this as well, so that variance will converge to the product, the numerator and the denominator, so that the variance will be this. Okay, so that's the generalization of it. What if we want to see an application? This is a problem. A production robot was built to produce 1 million tons of product annually, blah, blah, blah. It was, but because of lack of, irregular supply of raw materials, it produced in the first year 900,000 tons. In the second year, it was found that it's 9/10 of the past year's output, and it continues in that fashion, meaning that is 9/10 of what was produced last year, 9/10 of what was produced last year, and it continues in that fashion. Now, the questions are now, what will be its gross product throughout its existence? What will be its gross product? 2, what will be its EAP, expected annual production? 3, what will be its annual production variance? How will you place a 95% confidence interval on its EAP? You would find this tasking if you are not fully aware of technique of this method. You will notice that it is very easy to see anyway that this will be the series that describes the production pattern of the annual production series for the robot. Consequently, its gross will merely be the sum to infinity of this times that. All right. So we saw that the sum to infinity of this is 9. So times that will give us the gross product to be this. Okay. If you go back to slide 6, type 9, you see that you get solution. The result there will be applicable here. Okay. So meaning that we will use that result to calculate the average production, EAP to be 10⁻⁷, the average production variance to be this, and the 95% confidence interval on this AP will be this tons. Comment: the technique allows one to use more, method of solving GPs and DPs as it suits the problem. So you have a lot of ways through which you can handle the problems in there. Note that we did not need its year of existence. And that may not be available except if you want to take this year of existence to terminate at where the point converges. And this makes programming easy. It makes programming easier because if I know the property of the discrete distribution, the distribution DD, I don't need to be writing loops upon loops upon loops. I know that the mean will just be the numerator times the denominator. I'll put it there. So I will save the processor's time. I won't give it tasking arithmetic. This is the farthest I intend to go on this issue. Watch out for my next video. Please like, share, and subscribe. Thanks for listening. Thank you. See you next time when I come up with something else. Thank you.